So today we want to talk about continuity of functions. What does it mean for a function to have continuity at a point? Or in other words, what does it mean for a function to be continuous? In order for a function to be continuous at a point, it must satisfy three conditions. The first condition is that f of a must be defined. The function must have a y value at the point you are testing for continuity. The second condition is that the limit as x approaches a from the left of f of x must equal the limit as x approaches a from the right of f of x. So your left-hand limit and your right-hand limit must be the same. The third condition is that the limit as x approaches a of f of x is equal to what f of a is defined to be. So your limit and the value of your function at that point must be the same y value. We refer to this as the three-part definition of continuity. You need to know this definition and be familiar with it, as well as know how to use it to determine continuity. So let's look at some examples of continuous functions. The function that we have here on the left is a continuous function. If I trace the path of the graph with my pencil, I don't have to ever pick up my pencil to draw a different part of the graph. This is an easy way to test to see if a function is continuous, although it will not count as a mathematical reason, a mathematical justification for a function to be continuous. If you look at the graph on the right, I can trace the path of my graph until I get to x equals 2. Then I have a hole there. I have to pick up my pencil and start drawing on the other side. So this function is not continuous at x equals 2. It is continuous at other places, for example at x equals 0, because at x equals 0, the limit from the left and from the right is equal to 3. And so is the value of the function at f of 0. So you can have a function be not continuous at a point, but be continuous everywhere else on the graph. So let's determine if the function is continuous at the following values. If not, explain why it is not continuous. Part of our explanation needs to include what part of the three-part definition of continuity this function is not satisfying. So if you look at x equals -8, I want to look at this point here. I can see that that point is defined. So I have a value of the function at -8. This value is 3. And if I look at my left-hand limit, that is approaching 3. And my right-hand limit is also approaching 3. So this function is continuous at x equals -8. If I look at x equals -5, the value of my function at -5 is actually at 7. So this function is defined at -5 as having a y value of 7. But the limit from the left and the right is equal to +1. So because the limit does not equal where my function is defined, this is not continuous. So I need to write not continuous, and then my explanation state because the limit as x approaches -5 of my function does not equal the value my function is defined at. Make sure you are using proper notation for your limit. Let's look at x equals -3. For x equals -3, my left-hand limit is going to -infinity, my right-hand limit is going to -infinity, but I have a vertical asymptote at x equals -3. So my value of my function, f of -3, is not defined at -3. So this is not continuous because f of -3 is not defined. As soon as one of the three parts of your definition is not met, you can automatically say that the function is not continuous. Let's look at x equals -2. I have the function defined as -2 at -5. The left-hand limit is approaching -5 as well as the right-hand limit. So because the limits are equaling the same value as where this function is defined, I can say that this function is continuous at the point x equals -2. If I look at x equals 1, I can see that my left-hand limit is approaching -2 and my right-hand limit is approaching 1. So because those limits are not the same, this is not continuous because the limit as x approaches 1 from the left of f of x does not equal the limit as x approaches 1 from the right of f of x. Again, make sure you use correct limit notation when you write your statement. All right, let's look at x equals 5. At x equals 5, there's not a dot on my graph, but there's not a hole or an asymptote to indicate anything out of the ordinary. So I know that this function is defined at 5, 3. My limit from the left is 3. My limit from the right is 3. So because my limit is the same as the value of my function, I can say that this is continuous. So that's how you can determine continuity based on a graph. What if you are given the equation? For example, f of x equals -x cubed plus 3x squared plus 2 at x equals 5. Well, I could make a graph of this function. I could make a table of this function. But another property that we know is that anytime we have a polynomial, which is what f of x is, those functions are continuous everywhere. They don't have any holes, they don't have any jumps, they don't have any asymptotes. So they are what we call continuous everywhere. So the limit as x approaches 5 for f of x is going to be the limit as x approaches 5 of what this is. I can use direct substitution. So -5 cubed plus 3 times 5 squared plus 2. If I type that into my calculator, I get that this limit is equal to -48. If I evaluate the function at x equals 5, I can also see, let me plug in 5 for x, that my function is defined at -48. So, since the limit as x approaches 5 of f of x equals f of 5, f of x is continuous at x equals 5. And I can also state because f of x is a polynomial function, so linear functions, quadratics, cubics, any of those are polynomials. Exponential is also continuous everywhere. Because it is a polynomial function, f is continuous everywhere. This doesn't use our 3-part definition, which is why I needed this top part, but you can conclude that if you have a polynomial function, it is continuous everywhere. What if you have a piecewise function? Everyone's favorite. Well, then I need to test my left and my right-hand limit. Well, here I want to find the value of my function at x equals 1. Well, that just happens to be where my function changes and how it's defined. So, to find the value of f of 1, I need to use this top part of my function. So I have that f of 1 equals negative 1/2. I also need to find the limits as x approaches 1 from the left of f of x, and the limits as x approaches 1 from the right of f of x. To find the limit as x approaches 1 from the left of f of x, I need to use the part of my function that is defined for values of x to the left of 1. So for x values such as 0, negative 1, negative 2. Well, those values would be defined with this function. So I'm going to use negative x over 2. So I need to find the limit as x approaches 1 from the left of negative x over 2. And I can use direct substitution to evaluate this limit. And so I would get negative 1 over 2. Okay, but I can't just say that my limit is going to equal negative 1 over 2 because I don't know what's happening from the right side. I need to find that value as well. So for the right side of my function, I need to use the part of my function that has values for x greater than 1, such as 2, 3, 4. So that would mean using the second part of the function. So I need to find the limit as x approaches 1 of 2x plus 5. And again, I can use direct substitution. And when I use direct substitution, I find that my limit is equal to 7. Well, this creates a problem for continuity because my left-hand limit is not the same as my right-hand limit. So I can say that this function is not continuous at x equals 1 because the limit as x approaches 1 from the left of f of x does not equal the limit as x approaches 1 from the right of f of x. It is possible for this function to be continuous at other places. For example, this function is continuous at x equals 0. Don't believe me? Test it out using your three-part definition and see if all three criteria are met. Now that you know something about continuity of functions, good luck finding whether functions on your worksheet are continuous.